In this video lecture, we're going to start talking about the inclusion-exclusion principle. The inclusion-exclusion principle will help us count the number of elements in the union of two or more sets. And then, when we start talking about complements, it'll help us count the number of elements in the intersection of complements of sets. Here's the basic principle, and it all can be illustrated very nicely using a standard Venn diagram. We'll take the convention of calling our sets, or naming our sets with capital letters, such as set A, and here we have set B. And I think all of you recognize from seeing Venn diagrams in the past that this region here, which is in both set A and set B, is the intersection of AB. I'm going to introduce the notation that is used in our book. A intersect B is often just in our book referred to as AB. So we'll use this product notation to denote the intersection A intersect B. Now, A union B denotes every element that's in either set A or set B or both. It's this large region. It includes everything that's in at least one of the two sets. And the question is, how can we talk about the number of elements in this union? Well, we're going to use this notation to denote the number of elements in the union. That should be just a regular union sign. No stem on the U for a union sign. So this will denote the size of the union of A and B. And one might think initially, if you want to know how many elements there are in this union of A and B, you can start by just asking what's the number of elements in A, which we'll denote like this, the size of A, or the number of elements in the set A, and we'll add to that the number of elements in B. But what's the problem with this? Well, elements in this region have been counted once, just when we count here the number of elements in A. Elements over here have been counted once, but if an element is in both A and B, it's counted twice, once in this number, the number of elements in A, and it's counted once in this number. So it's double counted. And if I want the correct value for the size of the union, I have to get rid of that double counting. So I have to subtract the size of the intersection. And this is our basic formula for counting the size of the union of two sets. And this one basic formula is really at the heart of what we call the inclusion-exclusion principle. We include the sizes of both sets, the size of A and the size of B, but then we exclude what's been double counted. Now, how does that generalize? We're just going to get started generalizing that to more sets. Let's look what happens if we have three sets. Let's say here's set A, here's set B, and here's set C. I'm just going to erase that up there. And now we see here, there are many different regions. I'll show you some examples here. Everything in this region here, for example, is in A intersect C. We'll just write AC for that. Everything in this region here is in BC. And I won't shade it in, but that's the region AB. Now this region here, that's in all three sets, is in the intersection of A, B, and C, which we'll call ABC. Our question will be, how do we count things in the union A union B union C? Well, again, we might just start saying, if I want to know the size of the union, just add up the sizes of the three sets. The size of A plus the size of B plus the size of C. But then you say everything here in AC, in both A and C, has been counted here twice. So I would have to eliminate that, remove one of them so that things in here are counted properly. Things here in BC have been double counted. Things here in AB have been double counted. So I should eliminate AB, AC, and BC. But now there's a little problem that's remaining. Imagine something that's in all three sets, A, B, and C. We've counted it 3 times here because it's in A, it's in B, and in C. If it's in A, B, and C, we've removed it 3 times because it's in AB, it's in AC, and it's in BC. So something that's in this intersection of all 3 sets, A, B, C, has in the net total not been counted at all. So we really have to put it back in. So I'll just add back in the size of A, B, C. And this is our formula, the inclusion-exclusion formula, for the size of the union of 3 sets. You add up the sizes of the individual sets, you subtract the sizes of each intersection of a pair of sets, but then you have to put back in the size of the intersection of all 3. And you can check that that properly counts any element. If you have an element that's not in any of the sets, it won't be counted anywhere here. If you have an element that's just in A and not in B or C, it'll be counted here and nowhere else. In other words, it will be counted once in the union, which is what it should be counted. If you have an element that's just in C or just in B, again, it will be counted just once and nowhere else. If you have an element that's in both A and C, in this region, say it's in both A and C but not in B, then it will be counted twice here, but removed once for a net total of once, which is what we want it to count. If you have an element in A and B, but not C, or in B and C, but not A, that's over here, it will be counted again exactly once. If the element is in all 3 sets, it'll be counted 3 times, it'll be removed 3 times, and then it will be put back in once. In other words, it will be counted a net time of once, which is correct. Examples, we want to be able to talk about complements. So let's talk about De Morgan's laws. Now, first let's show you what it means to be a complement. Imagine all of our sets live in some larger set, which we call the universe. We'll always denote the universe by U. And if we have a set A within the universe, things in this set, those are things in A, things outside of the set will be denoted A complement. Now, people often use a bar to denote complement or a little C in the superscript, but in our book, complement is always denoted here by a prime. So A prime will denote A complement, or the complement of A. Now, if we have 2 sets, for example, here's A, and here's B, and here's our universe U, we already know that A union B is this set. So the stuff out here is A union B complement. And the first of De Morgan's laws says that if we want the complement of the union of A and B, that's the same as the complement of A intersect the complement of B. A prime intersect B prime. Now, what would that look like geometrically? Let's first put in A here. This is A complement. If we put in B here, B complement, I'll try to use horizontal lines here, is everything that's not in B. And if you look at stuff that's in both A complement and B complement, you'll see it's exactly the stuff that's outside both of the sets. In other words, outside of A union B. That shows you De Morgan's law holds. Another way to see that is to ask yourself, what does it mean to be in the complement of A union B? That means an element has to be not in at least one of A and B, because A union B is the set of things that are in at least one of A and B. So if an element is not in at least one of A and B, it certainly has to be not in A. Additionally, it has to be not in B. In other words, it has to be in the intersection of things that are not in A and things that are not in B. So any element that's in this complement of the union is in the intersection of the complements. And the other way around, if you give me an element that's in this intersection of A complement and B complement, then that means it's definitely not in A and it's definitely not in B. Both have to be true. And if it's neither in A nor in B, it's not in the union. So it's in the complement of the union. These two sets are identical. If there were a better picture here with nice shading, you would see that. I could probably should have used colors here, but I'll leave you to draw a nice colored picture showing this De Morgan's law. Now, De Morgan's law doesn't work only with two sets. It works if you have three sets. For three sets, you would write A union B union C. The complement is just the intersection A prime, intersection B prime, intersection C prime. And it doesn't just work for three sets, it works for 4 sets or 5 sets, or an infinite number of sets. In fact, if you study set theory, you see, for really exactly the same reason, it generalizes to arbitrary unions. It can be a union over a huge collection of sets. The complement of that big union of sets will just be the intersection of the complements of each of the individual sets. Now that's the first of De Morgan's laws. The second of De Morgan's laws says much the same thing, just kind of with everything flipped. It says the complement of the intersection, and let me get rid of some of these drawings so we can see that picture a little better. The complement of the intersection will actually be the union of the complements. A intersect B prime will equal A prime union B prime. Let's see what that looks like here. Here we have our universe, U. Here we have A, and here we have B. A intersect B is just this little bit here. So that A intersect B complement is everything here in the entire universe except this union, this intersection, A intersect B. So it's literally everything out here that's not in that little piece there. That's A intersect B prime. Well, that's the same as first taking everything that's in A complement, that's everything outside of A. I'll shade in everything that's outside of A. And then also shade in everything that's outside of B. And you'll see you've shaded everything except this blackened region. Let's be a union. So that we see this other form of De Morgan's law also works. And just like the previous one, it can be generalized to arbitrary intersections and unions. The complement of an arbitrary intersection of sets is just the union of the complements. Let me show you our first example of using this. We're going to ask the question, how many strings are there of length 7 from a 3-letter alphabet, alpha, beta, gamma, which contain all 3 letters? Of course, we already know how to answer that. I'll just put a note here. The answer we denoted as T73. Now you could compute T73 in a variety of ways, but let's try to use the inclusion-exclusion principle to count the number of such strings. In order to do that, we're going to have to set up our universe. And here our universe U will be the set. Always define your sets first. It's a set of all 3-letter strings. I'm sorry, 7-letter strings from this alphabet. because everything we're going to talk about will involve 7-letter strings from this alphabet. Now, in order for this to be useful, you should always be able to count your universe very easily. Ask yourself, how many 7-letter strings are there from this alphabet? That will be denoted the size of U. That will just be 3 to the 7th. Now, what are our individual sets? Our individual sets will be the sets A, B, and C, where A will be the set of strings with no alpha. B will be the set of strings with no beta. And C will be the set of strings with no gamma. Now, why am I choosing my sets this way? If this is the first time you've seen this, it might seem weird to denote by capital A here the set of strings that have no alpha. Well, there are kind of two main reasons for this. The first reason, which is important, is that this is something we can count easily. What is the size of the set A? If you look at strings with no alpha, that means the strings just involve beta and gamma, a 2-letter alphabet, and they're 7-letter strings, so we can tell easily that they're 2 to the 7th strings in A. Similarly, the size of B is the same thing, and the size of C is the same thing. But that's not the only reason we choose A, B, and C like this. If it were just that they're easy to count, they still might not be useful. They're useful because the thing we want to find, so we'll always put this WTF. WTF always stands here for want to find. We want to find how many 7-letter strings contain all 3 letters. Well, containing all 3 letters means they're not in A, which means they're in A complement. And containing a beta means it's not in B. So it must be in A complement and in B complement, which means it's in that intersection, A complement times B complement. Remember, this will mean intersection when I just write one next to the other. And since it contains gamma, it will have to not be in C, which means it is in C complement. And so any string of length 7 that contains all 3 letters is in the intersection of the complements. And of course, we want to find the size of that intersection. Well, by De Morgan's law, the size of the intersection, or should just say the intersection of the complement, is precisely the complement of the union. Well, what do we mean by the complement of the union? We mean, let me write this, A prime, B prime, C prime is the complement of A union B union C. So what can we say about the size of A prime, B prime, C prime? Well, I just have to count how many things are in the complement of the union. Well, if I knew the size of the union, I can find the complement of the union just by taking the total number of strings there are and subtracting the number in the union. That's how you get the size of the complement. So I would just take the size of the universe and subtract the size of the union. And remember, we had an inclusion-exclusion principle already for the size of the union. That's the size of U minus, to get the size of the union, we have the size of A plus the size of B plus the size of C minus the size of AB minus the size of BC minus the size of AC. And then remember, we had to put back in the size of ABC. So all of that we're subtracting from the size of the union, of the universe. And now we can just fill in the numbers. The size of A prime, B prime, C prime is the size of the universe, that's 3 to the 7th. And we subtract the size of A, which is 2 to the 7th, plus another 2 to the 7th, plus another 2 to the 7th. So we have 3 times 2 to the 7th. Then from that, we subtract the size of AB. Well, what does AB mean, the intersection of these two sets? A string is in AB, meaning the intersection of A and B, if it has no alpha and no beta. Well, what 7-letter strings have no alpha and no beta? It can only be gamma, 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 gamma. There is only one such string. So this size of AB has to be 1. And the same is true for the size of BC, because a string is in B intersects C. If there's no beta and no gamma, it can only be all alphas. And the size of AC, similarly, is 1. So I'm going to have 3 for, there's -1, -1, and -1. That gives me -3 total. And then we have to put back in the size of ABC. Well, what's the size of ABC? How many 7-letter strings have no alpha, no beta, and no gamma? It's in all of those. Of course, there are none. You can't have a string, a 7-letter string from that alphabet with no alpha, no beta, and no gamma. So this is really all we have for our computation. In other words, we have 3 to the 7th minus 3 times 2 to the 7th, then plus 3, and that will be equal to, what do we have here? That will be equal to 2187 minus 3 times 128, that's 2 to the 7th, plus 3, and we'll end up with exactly 1806. Now, I hope all of you actually have your big T triangle handy, and you'll see that T73, which you could have computed just with the recursive formula and your T triangle, is in fact 1806. And this was just another way we can compute that.